Yeah, in this video, I'm going to be talking about matching and allocation problems, as well as how to solve them using something called the Hungarian algorithm. So let's just have a think about what are these about. So allocation problems, it's things like if you think about a school, they've got all these classes and all these teachers, they have to match them up so that, you've got one teacher to each class, or you might think about in a business, a similar thing of staff and kind of jobs to do. One way to do that is represent things as a bipartite graph. That means that there's two separate groups, two different parts, and vertices within a group are never connected, but there are connections between one group and the other. So of the two groups, connections between them, but no other way. If you've got a complete bipartite graph, then all the vertices of one group are connected to all the vertices of the other group. So yeah, allocation problems generally look something like this. You've got some bipartite graph and you've got different weights often on the connections between them. That might be, the time it takes people to do different jobs. What you want to do is minimize the overall time, so find the best possible allocation. So how do we do this? Well, let's just first do a nice simple example of what this might look like. So if you want to pause the video, give this a read, you can get a bit of a flavor of what we're doing. But basically, we've got these teachers and different subjects for them to teach. And let's have a little draw. So I'm going to draw one group being the teachers. So each of those letters representing a teacher, just the first letter of their name. And then our different subjects that they can teach. There's board games, there's rock climbing, there's cereal preparation. And is that it? No, and there's origami. Okay, so now if we draw this bipartite graph, we can work out, okay, so Mr. Middle, he can teach board games, so he's connected to that, connected to rock climbing and cereal preparation. Mr. Hughes is just origami and cereal preparation. Mr. Christo, rock climbing and board games. And then Mr. Long, just board games. Now, if you think about allocating this, perhaps my graph is not that helpful to do that, but one thing we can notice is L has to be connected to B because that's the only thing that teacher can teach. So, if we want everyone to just teach one class, well, that's what they're going to get. So if we think about that, okay, so no one else is going to teach that. What do we got left? So Mr. Christo here, he can either do board games or rock climbing. So board games is out. So what Christo is doing rock climbing. We can do it here. So he's teaching that. He's teaching that. And then, oh, in fact, my apologies. And then for, what have we got left? So we've got Mr. Middle here. He could only do rock climbing, board games, or cereal preparation. So he gets cereal preparation because the other ones are taken. And then that leaves Ms. Hughes with origami. So maybe it's a bit easier to see with a better drawn one of these graphs. Let's see if my better drawing makes it clearer. Perhaps it does, especially now that, you can see, well, L has to be the one who gets to do B because that's the only thing they can do. And then you're kind of just eliminating the other things. So, that one, not too hard to solve in a way, and we're kind of almost doing it by inspection there. But sometimes we have these weights, and, so it might be the time it takes jobs to be done or the cost of something being done. And then it becomes more complicated. And so it's worth having an algorithm to do that. The algorithm we have for this is called the Hungarian algorithm, named after these two Hungarian mathematicians. And yeah, I have in my slides here a pretty detailed explanation of how it works. So what you might want to do is just pause the video to have a read through of this if you want to see the long version. I've also got the short version in a few slides' time, which is what I'd recommend you put in your bound reference. So chance to pause it, and then I'll go on to the next slide if you want to read all of that. So here's the rest of my long version. So again, a chance to pause it if you wanted to read all that. But yeah, here is what I would say is worth putting in your bound reference. It's, I call it the short version. It's still not that short really, but if I'm doing one of these problems, here's what I refer back to when I'm doing it. So definitely pause the video and give that a read so that you feel like you might start to understand it. Then I'll do an example where I'm referring back to this and hopefully that really cements it. So here is my example. again, I would suggest probably pausing the video, giving it a read, just to understand the flavor of the example. And then I'm going to jump into doing this algorithm. Okay, so hopefully you've had a chance to read all that. What I've done is, the first thing I've done is I have in my little whiteboard here, just taken out the key information. Okay, so what we need to do is we need to just follow the algorithm, and then eventually we'll end up with lots of zeros and it'll all work out really nicely. Let's have a look. So we're subtracting the lowest value in each row from every element in that row. So if I think about doing that, I might just redraw here. So we've got G, L, C. And so for row A, we have the first, so the lowest element is 200. So 200 subtract 200 is 0. 250 take 200 is 50, and 320 take 200 is 120. This next row, the lowest value is 250. So this first bit's going to be 30. I'm going to get 50. I'm going to get 0. And then for this one, our lowest element is 300. So that will be 0, but this will be 170, and this will be 210. Okay. The next step that we're kind of continuously doing is we're drawing lines where we're trying to draw the minimum number of lines to cover all the zeros in our table. What you'll see is the minimum number is 2, but there are actually 3 allocations we need to do here. So we need to keep going. We need to do the next step in our algorithm. You know, if you're lucky, it'll just stop there. We will have already been able to do our allocation, but in this case, no. So now we've got, if a column doesn't contain a 0, subtract the lowest value from every element in that column, including from itself. So I'm just going to redraw it. So we've got A, B, C. Yeah, maybe we'll try a different color here. A, B, C. And we've got G, L, C. So what we're subtracting, the value of each of every column, including itself. And yeah, so, but only if that column doesn't contain a 0. So the only one that doesn't contain a 0 is that first one. So we've got 0, 0, what will that, sorry, not the first one, the second one, 120. And then, so these columns just stay the same. And then we just have a look to see, is that enough for our allocation? Change back to red. So what? The minimum number of lines, I reckon we could do, yeah, I think it's going to be 3 really, because we could do kind of that. And I don't really see a better way to do it. So now we've done that, that's great. We can draw our bipartite graph. And the way the bipartite graph works for our allocation is anything that's got a 0, that is a connection one side to the other. So we've got, okay, so A is connected to G and L. B is connected to L and C is only connected to G. So what we can see from this is because C is only connected to G, that means for our optimal allocation, C will buy the food for G. Next, well, A is only connected to G and L, so A will buy L, and B will buy C. So overall, our people here are paying overall, what, 500 plus 300, 800 overall. That's the cheapest they can get. And yeah, we've done that allocation. So yeah, look, it's not particularly easy, is it? But we have gotten there. Now it gets even harder sometimes. So that one, you know, as Hungarian algorithms go, worked out quite nicely. We've got another one here, which we'll give a go. And this one, unfortunately, will take us even more steps. So I just clear my whiteboard here. And we'll have to copy it over again. So if you'd like to give this a little read here, you could pause the video and give it a read, understand a bit of what is being asked. But basically, we're just trying to do the Hungarian algorithm on the table down below. So again, we've got A, B, C, but up the top, we've got V, D, J. So let's put that in. Okay, so I've put that information in. And now if we think about our first little bit of doing this algorithm, maybe we should just go back to our short version. So we're just subtracting the lowest value in each row from every element in that row. So if I think about that first row, what are we going to end up with? We will have, so the lowest value is 22. So that first bit of our table will be 7, and then 15, and 0. Our lowest one's 26, so that'll be 0, 1, 6. And then here, 25 is our lowest. So we've got, what, 9 here and 8 here. And what we can see is if we then check what's our minimum number of lines, it's just 1. So we got to go on to the next part of our algorithm, which is where if a column doesn't contain a 0, we're subtracting the lowest value from every element in that column. So just draw in this again. We've got, okay, so 6 is the lowest value in that column, so this becomes, no, just 1. 1, 0, and 2. We get 8 here, 0 here, and 14 here. And these don't get changed, they're just still zeros. Next, we do that same thing that we always do, which is we check, okay, what's our minimum number of lines? Perhaps you can see it's 2. Now for our allocation, we need 3 of these lines. So we do the next bit, which is a bit of a funny step. We're adding the smallest uncovered value to elements that are covered by 2 lines, if there are any. So let's do that. There's only one spot that is covered by 2, which is this bit. So what do we get? We're adding the smallest uncovered value to that. So if we draw our next step in our algorithm, that one is going to, what the smallest one is 1. So that gets to be 1. What else do we have to do? We subtract the smallest uncovered element from all uncovered elements. And we just keep repeating this step as necessary. How good. So the smallest value is 1. And so every uncovered bit gets 1 subtracted from it. And so that is going to become a 0. That'll become 13. These just stay as all zeros. This becomes 1. This becomes 7. Now I think hopefully we're all done here, because I reckon the minimum number of lines is now 3. So we can start doing that bipartite graph and allocate away all of our taxi rides. So what? A is connected to V and J. B is connected to V and D. And C is connected to just J. So from that, we can go, okay, so what? The only 0 we get for C is with J, so they've got to go there. And then A must go with V because they just had J and V. And so B is going with D. So our overall cost for that, all those taxi rides, is all those numbers added up. So we'll look at what that is. So lots and lots of process here. So overall, it adds up to 81 euros. Yeah, okay.